Hello friends, welcome to Ship Stability Chapter 4. Today we will discuss about displacement of the ship, light displacement of the ship, load displacement, present displacement, dead weight abroad, dead weight available, waterplane area, waterplane coefficient, underwater volume, block coefficient, reserve buoyancy, tons per centimeter or TPC. Okay, so if any of you want to directly access any of these topics without watching entire video, I will be writing the time for all these topics in the description box. Okay, now let's go to the chapters. Okay, so what is displacement? Okay, so displacement is commonly used for denoting the mass of the ships. Okay, that is measured in tons. Okay, so from our previous chapter, flotation and all those things, so displacement is the water displaced by the floating object when it is floating on a liquid. So when to find out the weight of that floating object, we need to find out the mass of the water. Okay, so mass of the water will be volume of water into density of the water. Okay, so to get the volume of the water, it is better to find out the underwater volume of the object. Okay, so in this in this diagram, this is an object and then this shaded area is the underwater volume, and this is floating on a water, and it is having 10 meters draft and 20 meters wide and 100 meters length. So it is a box shaped vessel. So underwater volume of the vessel will be 100 meter into 20 into 10. Okay, so that would be 20,000 metric cube. Okay, so depending upon the whether the vessel is floating on sea water or fresh water, we have to multiply with the density of the water. Okay, so when we multiply with density, if it is fresh water, then it will be 20,000 ton. So displacement we can be found out underwater volume of the object into density of water. Okay, now what is the light displacement of the vessel? Okay, so as we know that displacement is the mass of the ship when it is floating freely on the water. So what is a light displacement? Light displacement is basically nothing. It is the mass of empty vessel. Okay, empty means that the empty ship doesn't have any cargo, no fuel or lube oil or ballast water, fresh water, no stores or no passenger or no crew. So as when the ship is just built and only the machinery and the structure of the ship, So weight of that entire steel structure of the ship, that is called light displacement. Okay, without any of the cargo fuel and all those things. Okay, now the next thing is load displacement. So what is load displacement? So in this ship, when vessel is loaded with the cargoes and it is floating in salt water at summer draft, okay, and the vessel is floating in salt water, okay. Okay, so at load when the vessel is floating at summer draft in salt water, okay, the displacement of that vessel is called load displacement. Okay, so that means when the vessel is fully loaded, or when the vessel is floating at the summer draft in sea water, is called load displacement. So this load displacement is mainly used for the calculation how much cargo the vessel can load. Okay, so depending upon the load displacement, the chief officer will plan how much cargo vessel can carry at the time. Okay, so the another thing is present displacement. So the load displacement is what is the maximum weight of the ship when the vessel is floating at summer draft. Okay, so the present displacement means the vessel, right now we are not floating at a summer draft. Right now the vessel is floating at a draft which is below the summer draft. Okay, so at that time what would be the displacement of the vessel? So when the any time the displacement of the vessel when the ship is floating at any other draft other than summer draft. Okay, that is called present displacement. That means at present what is the draft and what is the displacement. So that is what is given here. Okay. So to find out the present displacement, so to find out the present displacement, we have to add all the cargo which is already present on board. Okay, cargo and all the water and all the stores, plus what is the light displacement. Okay, so empty mass of the empty vessel plus whatever the cargo is present on the ship. So we will get the present displacement of the ship. So present displacement is equal to sum of light displacement plus cargo and other substance on board. Okay, that is a present displacement. Okay, now another important thing is dead weight. So dead weight is actually the total mass of cargo. Okay, so total, okay, so total mass of cargo, fuel and fresh water, okay, everything that ship can carry when the ship is floating in salt water at summer load line. Okay, so that is the explanation of dead weight. So total mass of cargo, fuel, freshwater, everything that ship can carry at summer load line. Okay, so that is what I explained here. Okay, so dead weight of the ship. Okay, so it can be found out using dead weight is equal to load displacement. Okay, load displacement means and weight of the ship when it is floating at the summer load line. Okay, so now the dead weight is the weight of the cargo and other things when ship is floating in summer load line. So to find out the dead weight, we have to find out the load displacement and subtract light displacement. Okay, this is the formula for dead weight of the ship. Okay, so if anybody says the dead weight of the dead weight is 10,000 ton, that is not exactly the load displacement. Okay, load displacement will be higher than the always higher than the dead weight, because to get the load displacement, you have to add the light displacement along with the dead weight. Okay, so if I say the dead weight is 10,000, that doesn't mean that it is only the quantity of the cargo. It is it is the quantity. It may be the quantity of ballast, freshwater, fuel, etc. Everything at include at that ship on board that ship when it is floating at summer load line. Okay, now the another topic is dead weight abroad. Okay, so it is the total mass of cargo, fuel, freshwater, etc. on board at present. That means vessel is right now floating in at a particular draft. Okay, and it is not the summer load line is above that. Okay, at present vessel is floating. Okay, so and it is having ballast water, fuel oils, fresh water, everything. So the total weight of all the cargo, fuel oil and ballast water and fresh water, everything on board at the present draft. Okay, so that is called dead weight abroad. So dead weight abroad is the present displacement minus light displacement. Okay, so we discussed present displacement and light displacement earlier. So so subtracting those two, we will get the dead weight abroad. Okay, now the dead weight available means at present the ship is floating in a particular water level or have some draft. Okay, let's say a vessel's summer draft is 10 meter and a present draft is 9 meter. That means the vessel can load further go down further 1 meter. Okay, so that means the more cargo can be loaded on the vessel. So more cargo plus or some freshwater or whatever can be loaded on the vessel, so that it will reach the summer draft. Okay, so the difference between the displacement of the vessel at present and the load displacement, that is called dead weight available. So what is dead weight available? Load displacement minus present displacement. Okay, that is called dead weight available. Okay, now here is an example question. Okay, a box shaped vessel is 120 meters long. Okay, and 16 meters wide. Okay, and has a load draft of 8 meters. Load draft 8 meters, basically summer draft. Okay, that is this thing. And if the present draft is 6 meter, okay, that is this, then find the dead weight available. Okay, so dead weight available is the loadable displacement, or minus present, simply can say loadable dead weight minus present dead weight. Okay, so present dead weight can be found out using underwater volume of the vessel at present, okay, into density of the water. So in this question, it is not said that the vessel is floating in freshwater or anywhere. So in this case we will assume vessel is floating in salt water. Okay, so what is weird. Okay, present displacement. Okay, present loadable dead weight is equal to 120 into 16 into 8 meters into 1.025 tons. Okay, and the present displacement is equal to 120 into 16 into 6 meters into 1.025. okay, so the difference between these two, okay, okay, that will be the displacement available. Okay, so this thing we will get the answer as 1574 tons. Okay, and this one is equal to 11808 tons. Okay, so the difference between these two is 3936. So the dead weight available at this condition is this much tons. Okay, now next topic is water plane area. Okay, when the vessel is floating and the water line, this is the water line. Okay, so we have to assume that, okay, the water is cutting the ship into two pieces. Okay, the place where the ship is cut by the water line, so that plane, okay, that plane of the ship where the cutting happened is called water plane area. Okay, so when at a particular draft, let's assume this will be the shape of the vessel at the plane of the water. So it should look like this. Okay, so this is called the water plane area. Okay, now another thing is water plane coefficient. Okay, water plane coefficient, or it is also known as coefficient of fitness. Okay, so like I explained about the water plane area. Okay, so it is a water plane coefficient, that is a ratio of water plane area. Okay, this water plane area divided by the actual length and breadth of the ship at that particular draft. Okay, at that draft. Okay, so at a particular draft the vessel have an water plane area. Okay, so at that particular draft the actual length and breadth of the ship, okay, covering that water plane area. Okay, so when we take a ratio of that water plane area and the length into breadth or that rectangular box, we will get a value. So that thing is called water plane coefficient, that is mentioned as CW. Okay. Now similarly, like water plane area, there is something called underwater volume that we already discussed earlier. So again I will explain. Okay, so this is a ship floating in water. The volume below the volume of the ship below the water line is called underwater volume. Okay, so when we have to just to imagine or visualize the only or consider the only volume below the water line, so that will almost looks like this. Okay, so the volume below the water level, that is called underwater volume. So at any particular draft, the underwater volume will be different. Okay. So the another thing is block coefficient, or known as CB. So this block coefficient is also considered referred as coefficient of fitness of displacement. Okay, so similarly, like water plane coefficient, this block coefficient is the underwater volume of the ship, the ratio of underwater volume of the ship divided by the volume of the box containing that underwater volume. Okay, so underwater volume of the ship divided by length of the ship and breadth of the ship at that particular draft and the draft of the vessel. Okay, at that time. So that is block coefficient, that is CB at. Okay, so CB of this formula is also applicable for a tank. Okay, so tanks, cargo tanks or something have different shapes and volume at a different height. So this coefficient of block coefficient is also used for calculation of tank volumes. Okay, so in those case, volume of the tank divided by length into breadth into depth of the tank. Okay, now another thing is reserve buoyancy. Okay, so now reserve buoyancy is the volume. This green, this is the water line, and the volume above the water line of the ship. Okay, so that is not right at the moment, not submerged, but in future it will contribute to buoyancy. Okay, when the extra weight is loaded on the ship. So when we load the extra weight, the vessel will sink further. So the more buoyancy will be given by the volume which is at present above the water level. Okay, so reserve buoyancy. Okay, this reserve buoyancy can be defined as the volume of enclosed spaces above the water line. Okay, so why I say enclosed space? Okay, let's assume this compartment. Okay, so due to some accident, this compartment get bilged. Okay, and water is going inside this compartment without any restriction. Okay, so this much part of the compartment became open. Okay, so that doesn't count as enclosed space. Okay, so this since it is bilged and water is going in and out without any restriction, this doesn't contribute the buoyancy. Okay, so only the enclosed spaces will be able to contribute for the buoyancy of the vessel. Okay, that is why I written volume of enclosed spaces above the water line is called reserve buoyancy. That means that much space is reserved for future use when any extra weight is added on the ship. Okay, so this reserve buoyancy is also referred in percentage wise. Okay, so the percentage of reserve buoyancy, okay, is the ratio of total enclosed spaces above the water level. Okay, so total enclosed space above the water, okay, this green thing, okay, total enclosed space above the water divided by total enclosed volume of the ship. That means total enclosed volume of the ship. Okay, so whatever the volume above the water level divided by the whole volume of the ship, enclosed volume of the ship is called percentage of reserve buoyancy. Okay, now let's do a question. A box shaped vessel of 120 meter long, okay, and 14 meter wide, okay, and 12 meter high, okay, and displacement is 13776 tons. Find out the reserve buoyancy in sea water. Okay, so I forgot to mention something here. Okay, nothing. I'll explain. One moment. So in this question we need to find out the reserve buoyancy percentage. So previously we saw reserve buoyancy percentage is the total above water volume divided by total enclosed volume of the ship. Okay, so reserve buoyancy percentage, okay, so total above water volume, that is called reserve buoyancy, okay, divided by total volume of the ship. Okay, okay, so multiplied by 100, then only we get the percentage. Okay, so let's start solving the question with what all things we have. What we have is displacement. Okay, so what is displacement? Displacement is equal to underwater volume into density of the water. Okay, so we have what we have 13776, okay, is equal to underwater volume into 1.025. okay, that means underwater volume is equal to 13776 divided by 1.025. okay, that we get as 13440 metric cube. Okay, so there is a in question it is given as 120 meter is long, 14 meter wide, and 12 meter is the height of the vessel. Okay, so with all these things, if we multiply, we get the total volume of the ship. So total volume is equal to equal to 120 into 14 into 12. Okay, so that we will get us 20,160 metric cube. Okay, so let's go back to the equation once again. Okay, what is reserve buoyancy? Reserve buoyancy percentage is equal to RB by total volume into 100. So reserve buoyancy is the volume above the water line. Okay, so what we have here is total volume of the ship, volume below the water, that is underwater volume. So above water volume is equal to total volume minus total volume minus this underwater volume. Okay, so reserve buoyancy is equal to 20160 minus 13440. Okay, how much we get for that is equal to 6720 metric cube. Now what we have is above water volume, that is reserve buoyancy, total volume, everything is here. Now let's put everything in the formula. Okay, so RB percentage, okay, RB percentage is equal to reserve buoyancy, okay, 6720 divided by total volume is 20160, okay, into 100. Okay, so the reserve volume finally what we get is 33.33 percentage. Okay, that's all. So the next topic is tons per centimeter. Okay, it is also known as TPC. Okay, so it is the number of tons required to cause the ship to sink or rise by 1 centimeter at that particular draft. Okay, so at present vessel is floating at this water line. Okay, so what will happen if we put some load or tons of weight on the ship? Okay, so if we add weight, the ship will sink further and this will be the new water line. Okay, if we take the load of the ship will rise and the green line will be the new water line. Okay, so the difference between the present water line and the both the above and below. Okay, so to cause a change, okay, or a difference of 1 centimeter in the water line or draft. Okay, so to rise or sink the ship's draft by 1 centimeter. Okay, for that thing, how much load has to be added or removed from the ship? Okay, that is called tons per centimeter. Okay, so there is a derivation to how the TPC is calculated, and there is a formula also. Okay, so that formula is that we are going to explain here. Okay, so consider this is a vessel and that vessel is sinked by 1 centimeter. Okay, this is the water line and this is the new water line. Okay, okay, so the difference between these two water line is 1 centimeter. Okay, so let's assume the initial water plane area of the vessel, that is a square. Okay, so that is initial water plane area is a square, and since the vessel sink by 1 centimeter, okay, so there will be a change in volume. Okay, or the volume of the underwater volume of the ship will be increased, right? So because the vessel is sinking. Okay, so that volume is area, water plane area of the vessel multiplied by 1 centimeter. because area 1 centimeter is the height of the or the height of the box, or the if we assume this gap as a small rectangular rectangular cube or rectangular box, and this 1 centimeter is the height of that rectangular box, okay, and a square is the water plane area. So since the rise or sinkage is only 1 centimeter, we are assuming that the water plane area, initial water plane area will not change, okay, and that will be for 1 centimeter we are assuming the water plane area is same, okay. So the volume increased increase in underwater volume when the vessel is sinked by 1 centimeter, then that will be the initial water plane area into 1 centimeter, okay. So we can say as area is equal a square, instead let's give it as a only, not a square, okay, just for calculation purpose, okay. Area into 1 centimeter we can write it as 1 by 100, okay, 1 by 100 meters, right. So this total will be metric cube, okay. So increase in volume or increase in volume, after that what will be the displacement, increase in displacement due to sinkage, that will be increase in volume, okay, volume, that this one, okay. Increase in volume into density of water, okay. So increase in volume is this much, A into 1 by 100, okay, A into 1 by 100, okay. So the vessel is floating in sea water, then density will be 1.025, okay. So for the increase in displacement will be A divided by 100 into 1 by 025 tons, okay. So from this we can say the weight or tons required for sinkage of vessel by 1 centimeter is A divided by 100 into 1.025 in salt water. If the vessel is floating in fresh water, the density will be 1, okay. So in that case tons per centimeter will be A divided by 100 into 1, that is equal to A divided by 100, okay. And in salt water that will be A divided by 100 into 1.025, okay. So the next is I guess we have some problems, exercise problems, okay. Let's do that, okay. So the length and breadth of the water plane of a ship are 100 and 12 meter. If the coefficient of the thickness of the water plane is 0.7, find the TPC in salt water and fresh water, okay. So see the coefficient of thickness, water plane coefficient, okay. That will be, the formula for that is water plane area divided by length into breadth, okay. So here the water plane coefficient is 0.7 is equal to water plane area divided by length is equal to 100 into breadth is equal to 12, okay. So water plane area will be 0.7 into 100 into 12 meters, okay. that will be 840 meter square. Okay, what we need to find out is the TPC of the vessel in salt water. Now what is the formula for TPC in salt water is equal to area divided by 100, that area is water plane area, okay, divided by 100 into 1.025. okay, so water plane area we already have here, that is 840, okay, divided by 100, okay, into 1.025. okay, the answer will be somewhere around 8.610 tons. okay, the next is what will be the TPC for freshwater. So TPC in freshwater is equal to water plane area A divided by 100 into freshwater density, which is 1. okay, so 840 divided by 100 into 1, that is 8.40 tons. okay, so from this example only we can see this, for the sea water the TPC is higher than the fresh water. That means for the higher density the TPC will be higher. okay, okay, so next let's do some other problem. okay, then next thing, a ship is floating in dock water. The related density of the dock water is 1.010. okay, the draft of the vessel at that time is 5 meter. okay, so 90 meter long and 10 meter wide. okay, so the ship is 90 meter long, okay, 10 meter wide, okay, and it is the draft of the vessel is 5 meters. okay, this is water line. okay, draft is 5 meters. okay, if the block coefficient of the vessel is 0.72, okay, and the light displacement of the ship is 1200 ton. okay, find the dead weight abroad. okay, so what we need is dead weight abroad. So from the previous slides we know what is to find out the dead weight abroad. We need to subtract the light present dead weight, present displacement minus light displacement. okay, am I telling it correctly? Let's see the previous slide. okay, we can just confirm just for the dead weight abroad is the percent displacement minus light displacement. okay, okay, so what all things we are given and we will try to solve with that thing. okay, so present displacement is equal to how can we find out underwater volume of the vessel into density, correct, and what is the density right now is this much. okay, so let's find out the present displacement. So underwater volume will be 90 into 5 meter, that is the draft, into 10, okay, into 1.010. okay, that will be 3272.4 tons. okay, now the lightweight light displacement. Okay, so light displacement, they in the question already given us 1200 tons. Okay, 1200 tons. Okay. So what will be the dead weight on board? Okay, that is this thing minus 1200 tons. Okay, so how much it will be? 2072.4 tons. Okay, that is the answer. The next question, a ship is floating in fresh water, okay, at a draft of 6.8 meters. Okay, if the ship's maximum freshwater is 7 meter. Okay, so this is the present draft 6.8 and maximum freshwater draft is 7 meter. Okay, and the salt water TPC is 40. Okay, find the dead weight available. Okay, so what we have here, salt water TPC. Salt water TPC is equal to, what is the formula? A divided by 100 into 1.025. Okay, so the value, that value is 40 here, correct? So in this question, the things that we don't know is water plane area. So water plane area is equal to 40 divided by 1.025 into 100. Okay, so water plane area we get is 39.024 tons. Sorry, meter square area, meter square. Okay, so we need to find out the dead weight available. Okay, what is dead weight available? Dead weight available means the vessel is already loaded till the 6.8 meters and it can load till 7 meters. So 20 centimeter more the vessel can be loaded, right? So they are given the TPC, so they want us to solve the question using the TPC only. Okay, so since the vessel is floating in fresh water, so the remaining can be, so 20 centimeter. So for 20 centimeter to how much cargo we needed. Okay, so that is 20 centimeter multiplied by freshwater TPC. Okay, then we will get the quantity to be loaded for the vessel to reach a draft of 7 meters. So we need to find out the freshwater TPC. So freshwater TPC is, okay, area, water plane area divided by 100 into freshwater density, which is 1. So the water plane area here is 39.024 meters square. Okay, divided by 100 into 1. Okay, so freshwater TPC will be 0.392. Okay, no, I made a mistake. Sorry guys, the area is not 39.024, it is the 39, the area is 39024, not 39.0. it was just a writing mistake. Okay, so the at final what our TPC freshwater TPC will be 39.024 meter square. Okay, so that is the TPC freshwater TPC, and we want to find out the dead weight available is equal to 20 into 39.024, that is 780.48 tons. Okay, that is the dead weight available. So to reach the 7 meters we can load 780 tons. Okay, guys, I guess this is for this topic, and thank you very much for watching all this video. Thank you. Bye.